Hello, my name is Stefan Abgarian, and this is my presentation for assignment 2, in which I did Steam rating prediction. So, what is Steam for those that aren't aware? Steam is a digital storefront for video games created in September 12, 2003 by Gabe Newell. It contains games dating back to the 20th century with recommendations working on a yes-no system, where users either recommend a game or don't, while providing a text description. And here's an example of a Steam store page as well as some positive and negative reviews. So, the predictive task at hand. The objective was to create a model that is trained on player information and game metadata in order to predict whether a player will recommend a game or not. For evaluation, since the prediction task is a binary problem and there are several categorical and numerical variables, I believe logistic regression is the best approach for this problem. I will use F1, ROC plots, and precision recall to evaluate effectiveness. And for comparison, since I'm predicting a simple yes-no problem, 50% is a solid baseline that I will use for comparison, and if the model performs better than that, I know that it is useful. For validity, the data will be split into training and testing sets, and the accuracy of which it is able to correctly predict a player's recommendation being positive or negative will be the primary method of evaluation. So, exploratory analysis. For context, my dataset originates from Kaggle. It is a very large dataset consisting of player information including reviews, application metadata, and developer information. The creator of the dataset scraped the data used to create the set from the Steam API with the intention of helping people explore Steam's database. It includes over 200,000 applications and 1 million user reviews, and covers a time period from 1997 and is updated on a quarterly basis. It also contains publisher and developer relationship data and mapping information. The dataset was very large and consists of 49 different files. The main datasets were extremely large and had lots of missing info and nuances that made working with them very difficult. For example, some categories were in different languages, which made text mining difficult. There were also many missing or invalid values. Model and data exploration had to account for this. And there were also many unnecessary columns which clogged up the analysis process and made it difficult to analyze the actually important data. So, after adjusting the application's data to be able to merge properly with the reviews data, I did some basic exploratory analysis to understand some features about the data. After adjusting the columns and variable types, I merged the review and application's data together to make them easier to work with. I then analyzed the columns of the merged dataset to think about which columns would most likely be strong predictors for whether voted up, the column indicating whether a user recommended a game or not, would be true or false. Columns showing playtime, release date, required age to play, and whether the game was free or not, and several others seemed like strong contenders to me. I decided that for exploration, genre, category, and game developers would be an interesting point of analysis and could possibly make for strong predictors for a person's likelihood to recommend a game. I discovered that genres, developers, and categories were encoded across different files which I would have to map for EDA. First, I analyzed the number of each type of review. If there was too many positive or negative reviews, it could be difficult to create an effective model. Luckily, there was a good balance of about 75 to 25 in terms of positive to negative reviews, so I knew that a logistic regression model could theoretically work. I then wanted to see if playtime had an effect on whether a person would recommend a game or not. However, after comparing the playtimes of both the positive and negative reviews, I came to the conclusion that they were too similarly shaped for it to be a useful predictor. Next, I wanted to test if the game being free or not would have an effect. I predicted that a game would be more likely to have positive reviews if it was paid, but I was surprised to see that the proportion was nearly identical, so it wouldn't make for a very good predictor. Next, after analyzing the effect of release years on reviews, it gave me very interesting results. After about 2013, the number of positive reviews went up drastically. In addition, after 2005, the proportion of positive reviews plummeted before eventually steadily climbing back up again after 2014. I knew release year would be a strong predictor from this information. And here are some plots indicating this data. So for exploration, I looked at genres data. In particular, I wanted to see what genres had the highest number of positive reviews and highest proportion of positive reviews. So I made both a table and a graph for both these for easier visualizations. The table is on the right, and here is a graph. So I then wanted to perform the same analysis to look at category data. I was surprised by how many categories there were unrelated to the games themselves, like controller, support, and trading cards. Once again, the table is on the right, and here is a plot. And to conclude the EDA, I explored developer information. I was very surprised by how much the proportion of positive reviews decayed and how much they varied across Studio. I was also surprised to see what studios had high positive reviews. And here's a plot. And now let's talk about the modeling process. So for context, formulating this problem as a machine learning problem was quite simple. For this situation, I have a data frame consisting of a set of columns that all describe different information about a user and the game on Steam. I want to use those columns to predict the value of the column voted up, which will be either true or false. So for example, the inputs could be voted up, release year, required age, short description, Steam purchase, offer number reviews, offer playtime review, received for free, rendering early access, and the output will be either true or false as a predictor for voted up. Since the output is binary, I believe a logistic regression model will be best, and although naive Bayes and support vector machine models could be possible options as well, so I will analyze their pros and cons. All models have their pros and cons. For this model, naive Bayes, SVM, and logistic regression were viable options to consider. For naive Bayes, it's the easiest model to implement and the most efficient to train. However, it assumes that all features are independent given the label, otherwise it suffers from a double counting issue. Logistic regression fixes the double counting issue naive Bayes suffers from, however it's more expensive to train. And SVM models are non-probabilistic, so they optimize the classification error rather than the likelihood. With all this in mind, I decided logistic regression will be the best model for my data. With the columns that I had from the data and the data exploration I did earlier, I decided that release year, required age, short description, Steam purchase, offer number reviews, offer playtime review, received for free, and written during early access were going to be good predictors for voted up. So I started off by creating a data frame for them and cleaning them up as well as splitting them into a training and testing split. Now that I had the selected and split columns, I decided to do some more pre-processing on them to get them ready for the model. I used the TF-IDF vectorizer for short description to figure out if some words in a game's description will be more likely to lead to a positive review. I then used one-hot encoding for required age to make it work properly with the model since it's a categorical variable. I wanted to repeat the process using SVM to compare the results and see if a logistic regression model was indeed a better choice than an SVM model for this predictive task. I imported the corresponding library to speed up the process of the creation of the model, and aside from that, the process of training and using the model was largely the same as the logistic regression model. Finally, I wanted to use another logistic regression model, but with review text as a predictor. I originally excluded it since I believed it would be too strong of a predictor and too strongly corresponding with a positive or negative review. But I decided that for the sake of curiosity, I want to create a logistic regression model with it as a predictor and compares results to the previous two. I use another TF-IDF vectorizer for review text in this model. So, for evaluation. For my evaluation process, there are several different ways accuracy can be measured. The first is just plain accuracy from seeing how often the model predicted the correct status of voted up. While this gives a general idea of how the models function, it's pretty surface level and I want to evaluate the model's effectiveness deeper. So I also use a confusion matrix to evaluate each model's effectiveness. By seeing the amount of true positives, true negatives, false positives, and false negatives, I had a better idea of the model's effectiveness than just plain accuracy. I also used ROC plus to see how often the model would rank a random positive example higher than a random negative example. And using a confusion matrix, I was able to gather a lot of information about the model. The precision was able to predict how many predictions made by the model were actually correct. A high precision indicated that there were few false positives. Recall in a confusion matrix shows I was able to predict that of all the samples of positive reviews, how many did the model find. A high recall indicated that there were few false negatives. F's 1 score helped balance precision and recall. I was able to account for when the classes were imbalanced, and a high F1 score meant both precision and recall were high. Support helped me gain insight by seeing the number of samples used per class, making it easier to detect and understand class imbalances in the model. And there were several baselines that can be considered for evaluation whether the predictive model was good or not. An absolutely basic baseline without knowing any information about the data is that since I'm looking to solve a basic yes-no problem, 50% could be considered a basic baseline to aim for. However, after analyzing the data during my EDA, I discovered that about 75% of the reviews were positive, so 75% would be a more accurate baseline to try to overcome. I can say that my model surpasses this baseline if either the accuracy or the ROC surpasses this number. When calculating the evaluation statistics for the original logistic regression model, I was surprised by how low the accuracy was for the model. The accuracy of the model was only 0.64 and the ROC area under curve was only 0.69, which means that the model performed worse than using the 75% baseline. The precision for guessing false was very low, while the precision for true was high. This meant that there were few false positives for guessing true, but a significant amount of false positives when guessing false. The recall was also subpar for both true and false, which means that for both prediction categories there was a significant amount of false negatives, and the F1 score ended up suffering because of this. Next, I looked at the plots for the ROC curve and the precision recall curve, which helped me gain some interesting insights. The area under the ROC curve was 0.69, which indicated that the model often confused positive and negative reviews based on the provided features. The strongest predictor, review text, was intentionally left out of this model, so I expected the model to perform much better with it. The precision recall curve had an area of 0.86 under the curve, which indicated that when the model predicted a review was positive, it was usually right. This means that the model primarily suffered from having to predict negative reviews. And for the SVM model, I was surprised by how similar it was to the original logistic regression model. The results were within a few decimal points of each other, and I came up with a couple theories for why that was. Both logistic regression and SVM are fundamentally linear classifiers, and since the dataset was very large, I believe that they ended up converging on very similar hyperparameters for prediction. And because the features of both the models are linearly separable to a similar degree, both models ended up reaching a similar ceiling. And while not by much, the original logistic regression model had a stronger recall than the SVM, meaning that the SVM model had slightly more false negatives. And looking at the plots for the ROC curve and precision recall curve, I was able to tell that the SVM model suffered from largely the similar stuff and had similar strength as the logistic regression model. The area under the ROC curve was 0.69, which indicated that the model often confused positive and negative reviews based on the provided features, and just like with the original logistic regression model, the strongest predictor review text was intentionally left out. The precision recall had an area of 0.86 under the curve, which indicated that when the model predicted a review was positive, it was usually right, and this means that the model primarily suffered from having to predict negative reviews, just like the logistic regression model. And finally, for the logistic regression model that used review text as a predictor, I was surprised by how strong the results were. The accuracy of the model was 0.88, and the ROC area under curve was 0.95, which was just a significant improvement over the base logistic regression model, and significantly better than just a base case of 75%. The precision for guessing false was still a bit lower than the very high precision for true. This meant that there were very few false positives for guessing true, but just a few false positives for guessing false, but still more when guessing true than when guessing true. The recall was great for both true and false, which means that for both prediction categories there were very few false negatives, and as a result, the F1 score was great as well. And looking at the plots for the ROC curve and precision recall curve, I was able to see some more detail on how strongly the logistic regression model with review text performed. The area under the ROC curve was 0.95, which indicated that the model very rarely confused positive and negative reviews based on the provided features. So as expected, adding review text as a predictor vastly improved the effectiveness of the model. The precision recall had an area of 0.98 under the curve, which indicated that when the model predicted a review was positive, it was almost always right. However, as seen by the precision score, it still suffered slightly when predicting negative reviews. And so the conclusion that I had from the model is that I predicted from the start of my analysis that review text would be far and above the strongest predictor because there are certain keywords in a review that will be very strongly indicative of whether a person will give it a positive or negative review. A possibility for why the models performed poorly is that the dataset didn't have enough precise metadata features of the players and applications to accurately predict a review. Maybe with a more detailed dataset, a stronger model would be possible. Another possibility is that a game's review status is independent of most of the features outside of the game itself, in which case data about the game itself, such as its expected length, price, director, could help make a model that is able to much more accurately predict a review. From my models, I learned that most features about a user or an application store data aren't very relevant towards its actual review score, and for an analysis like that, it is better to search for other data sources that would contain more detail about the game itself that could be more indicative of its actual quality and review status. Now, let's talk about the discussion of related works. This dataset was used by both the author of the dataset and by several other people for their own purposes. The diversity of the dataset and the information it provides allows for many different nuanced studies of STEAM data. As far as I could tell, most of the other data analysis models used for this were for marketing analysis and analyzing trends in the gaming market instead of using the data as a predictive algorithm. And given the results of my models, it is reasonable to assume that the data would be better suited for analyzing trends and player preferences over trying to use it for prediction. On the author's GitHub, I found many different interesting graphs that gave insightful information on how the gaming scene has changed over the years and what trends the market has followed. For example, in the following heat map, we can see what genres often coincide with each other, which gives us insight into what games are popular and how often certain types of games are being made. For example, indie games that are casual and indie adventure games and indie action games are by far the most popular genre combinations. Something like a sports simulator is far less popular, which indicates that there is a smaller demand for these types of games, but also could mean that it's an underrepresented market with potential for growth. This, this graph analyzes the different genres of free-to-play games and how many there are of each genre. Indie is unsurprisingly the most popular since many indie developers make games out of love without a profit incentive in mind. Based off the heat map in the previous slide, we know casual and action games are often corresponding with indie games too, which shows a consistent trend. This graph uses Steam metadata to link a game to its actual numeric review on Metacritic rather than a simple yes-no review distribution, and then graphs it by game count. It is interesting how the common score range is 70 to 80%, which might coincidentally correspond with how about 75% of reviews were upvotes in the dataset that I used. Besides that, the data seems to follow a standard bell curve, so it could be interesting to make a model that predicts an exact score range rather than just a yes-no recommendation, if there is enough strong data available. This graph uses the Metacritic score of a game to see if a studio's quality of games increases as they release more games. An interesting thing to note is that while slight, the curve of the graph is positive, so there could be a slight correlation between average Metacritic score and the amount of games a studio releases that could be studied under a more detailed analysis. Next, this graph uses player recommendations as a primary metric and studies what genres were most recommended by players. Free-to-play seems to be the most popular genre by a long shot, which indicates that a game being free could possibly be more likely to receive a positive review from another player, which is something to consider for a predictive task, and especially interesting considering the results I found in my EDA contradicted this. Next, this graph visualizes how many games are released per year for a temporal analysis. It is interesting to note how approximately after 2013, the number of games being released per year sharply spiked upwards. This could be correlated to the rise of games in mainstream popularity during that time, and it could be an interesting metric to study for a prediction algorithm, since more data from a recent time period means that a model is going to be trained more on that data than other time periods. Now I will talk about how prior work approached this specific problem. Researchers Wenxiang Hu, Yimeng Wang, and Ruoming Xia looked to tackle a similar problem as me where they wanted to predict whether a game on Steam would be reviewed positively or not. Similarly to my study, they used a Steam Kaggle dataset, however their methodology was quite different. After cleaning the data, they at first went with a similar approach as me where they used logistic regression and SVM models. However, they later transitioned into using decision trees, gradient boosting, light gradient boosting machines, deep neural networks, and convolutional neural networks to get better results. The light gradient boosting machine gave the researchers the best results with an accuracy of 88.17% and an ROC area under curve of 80.36%. This is because the LGBM is able to effectively handle large and complex data sets thanks to its high efficiency and accuracy. And the final model ended up making use of tree-based algorithms for gradient boosting, as well as complex relationships between various different factors in the data. So, how did my results vary? Unlike the researchers, I used only logistic regressions and SVM for my models without complex data methodology. I also didn't use complex methodology like deep learning and gradient boosting for my model. The data that I used also didn't have pricing information on it, only whether the game was free or not, as well as other finer details that might have contributed to a stronger predictive model. Because of all these factors, their model ended up being much stronger than mine, but I was happy that I was able to gain insight on what it would take to make a more successful predictive algorithm and how their methodology differed from mine, and how that led to us getting different results. So, in conclusion, analyzing Steam review data and creating a predictive algorithm for it was a very interesting problem that has a lot of real world usages. It not only aids developers and publishers in calculating strategic planning and risk mitigation, but also could provide key information needed for game companies to know how to engage with their community to deliver the best possible experience. And even if my results weren't necessarily successful, I gained a lot of insight and understanding into the nature of review data and what kind of tools are needed to fully discover its patterns and trends. And here are the resources and works that I used. There's a Kaggle dataset, the research paper that was used to help make the Kaggle, the GitHub of the Kaggle creator, and the scientific article about the researchers I mentioned. All right, thank you very much.